I'm going to start with energy basics. It's kind of as detailed as we get into understanding what do we mean by energy and power, what are we talking about, how do we compare things, how do they differ. Here's what I'm going to talk about today. A little bit about what do we mean by energy and power, very lightly on thermodynamics, and then some of the important aspects of energy and energy resources and how we make them into useful forms. Okay, so starting here. What is energy and what is power? These are often used interchangeably, but they're not the same thing. And that's an important thing, I think, for you to get out of this class. Energy and power are two different things. Energy is actually the cumulative quantity, and power is the instantaneous use of the instantaneous flow. And so when we're talking about, your electricity bill or something, if you've ever paid an electricity bill, you're usually paying it in kilowatt hours. That is energy. That's a quantity of power times time that you've used over the month, right? It's a quantity of energy. The amount that you might be using instantaneously, like you turn on your microwave and it's suddenly using a kilowatt, that is power. That's like your flow. Okay? You will see them used, like I said, incorrectly in media all the time. The important thing to know is energy is just power times time. Now, the industry gets kind of lazy. You'll see this as several times in terms of units. Just to make things easier for energy industry, they often don't try to convert units all that much. So you'll see that on your electricity bill, for example, it's kilowatt hours, but a kilowatt is actually a watt is a joule per second. So you have two time elements in there, but they're whatever, the power's coming in kilowatts and the time is hours. And so we just multiply them together and have this mixed unit. It's still an energy unit. It's just energy times time over time makes it an energy unit. So you'll see your bills and things like that in kilowatt hours. You'll see this also in efficiency of power plants, which we're going to talk about. They're also mixed units, just because it's easier for the industry to not have to do unit conversions and stuff like that. We do make you do a little bit of unit conversions in this class, so look for that coming in some of your homeworks. If you're rusty on unit conversions, we have all sorts of math review sheets on that. But you'll find that a lot of times the data that you get is not in a useful unit, and so it's a useful exercise to do unit conversions. And remember how to do that. Okay, so just thinking about energy and power, these are just some easy analogies to help you think about it. Like I said, energy is like the accumulation, so you can think of it as like the accumulation of water in a bucket, where power would be the flow rate through the pipe. And so if the water's flowing through the pipe, that's the flow rate, that's the power. Energy is the accumulation in the bucket. Or you can think about it like a car. Energy would be the distance and the power would be your velocity. So just other ways to think about it. But these two things, like I said, are different, but are often used interchangeably in media. So you guys will be able to spot that. Okay, and then brief thermodynamics. For some of you, this will be really basic. Others may not have thought about thermodynamics since high school. So the first law of thermodynamics, hopefully you sort of remember this, conservation of energy. You can't create or destroy energy. You can convert it from one form to another, but the total quantity stays the same. And so this is an important aspect in thinking about our energy and our energy systems. And of course, we talk about energy consumption all the time. So what do we mean? When we're talking about our energy resources, that's a quantity of energy. And of course, that can be consumed, right? As you're converting it to other forms of energy, you're consuming the energy resource. So although energy itself is a conserved quantity, you can consume forms of that energy as you're transforming it to other forms. Importantly, if we can't create energy, why don't we run out of useful energy on Earth if we can't create it? It comes from the sun. We're constantly getting new energy from the sun. And we'll talk about that, and we'll look at our energy resources, but many of them are powered by the sun, with a few notable exceptions like geothermal and tides. But fossil fuels, biomass, wind, solar, those are all powered by the sun. So we're not a closed system. We're constantly getting new energy from the sun. So we're not running out. And we don't run out. We're not concerned about running out of our energy. Okay, so that's the first law. Second law is that there's always losses. I mean, if we're using heat to do work, it's lossy. You can't completely convert from one form to another. There's always going to be losses, and those losses are just, it's going into another form of energy, right? We're conserving energy, but heat cannot be converted completely to work. And we'll see that when we talk about some of our specific systems. Sometimes using heat for work can be very lossy in terms of getting the work we want out of it. And then more about the second law and the third law, thinking about energy systems, we're always increasing entropy. You don't really need to know more about that. It's just kind of for completeness. Energy is conserved in terms of its quantity, but its quality isn't always the same. And if you think about this is going to be intuitive. So we can lose the quality of the energy. And I have a simple example here to think about this, but quality is sometimes expressed as exergy, sometimes I just talk about it as quality, but it's basically is how useful is that energy? How much can we get out of it? What is the work able to do? So if you think about if I was holding a weight above the ground, it has a lot of potential energy. It's pretty high quality. I could do a lot of stuff with that weight that had potential energy. As I drop it, it has potential and kinetic energy. Now I can still do a lot with it. It's pretty high quality. Hits the ground, some of that energy is going to go into a low quality heat. It's not very useful. An even better example, I think, if you think about having a high temperature, very small quantity of high temperature energy versus like a huge quantity of low heat. That might be the same amount of energy, but you can do a lot more with the high temperature heat. Okay, so energy has quality, and that quality can be consumed, it can be lost. And so it's an important thing to think about why we might choose different resources, why we might value them in different forms. How useful are they? How much can we do with it? We've talked about already that energy resources are resources that are available on planet Earth. And they're what we're starting with in terms of thinking about meeting our energy services, right? Energy services are what we want: heating, lighting, manufacturing, transportation, etc. Right? This is the landscape of our energy resources on Earth. Again, most of them powered by the sun, including our fossil fuels. This is just, think about this as ancient biomass. Solar, wind, geothermal, and nuclear are some of the key exceptions where these are a stock resource, and this is from the heat inside the planet. And these exist in a bunch of different forms. We have radiant energy from the sun. We have gravitational energy from things like hydro and tides, chemical energy from our biomass and our fossil fuels, nuclear energy, of course, pretty obvious, and then some things exist as thermal energy. And so the interesting thing to think about is some of these we can use directly in their form, right? We use radiant energy for lighting all the time. That's a pretty simple one. We can use thermal stuff to provide heating services. When we do this, we don't have to do as many conversions. We have less losses typically. A typically more efficient way of using our resources is to use them directly because you don't have those losses in conversion. We can convert some of these other resources into thermal energy, use them directly, or we can do make it into a mechanical energy because we need that, or we make it into electrical energy. So just giving you a sense of this is what we're doing on a grand scale in order to provide those services we want. We're transforming to different forms of energy. Some of these are going to be high quality and some of them are lower quality, depending on what they are. All right, so one of the big questions I often get or people ask me about is okay, I know what our energy resources are, is can we provide, all of our needs with wind energy or all of our needs with solar energy, or what does it look like in terms of nuclear energy? So there's been some great studies on this, and this is just one of them. But just to give you a sense that in terms of our energy demand, both basically now or looking forward by estimates into 2040, we're not in a shortage of energy resources, and that would say for any of them. This study looked at what we could technologically recover, meaning with today's technology, with how we know how to get it, these are available energy resources to meet our current energy demands or projected energy demands from this study. There's two important columns here that is important to think about. These resources over here, which we call stock resources, these are the totals. This is the total amount available on planet Earth on human timescales. Because even though our fossil fuels, they're constantly being made, that takes hundreds of millions of years. So on human timescales, we have a stock. This is how much is available. But you can see it's a lot more than our energy consumption. For our renewables, we're constantly getting these. These are our flow resources. And so these are shown in resources available per year. And of course, the sun's kind of dwarfing everything, and the sun's really driving most of these resources. So it's just to give you a sense of scale, that it's not a challenge in terms of our decisions about our energy systems of a shortage of our energy resources. It's not a problem of running out. There are other reasons we decide to use one or the other. So the energy density also varies by orders of magnitude on our energy resources. I kind of gave you that sense when we were talking about E equals mc squared for our nuclear energy, super energy dense. We think about our energy density both in volume and by mass, and it depends on what we want it for. The obvious one that comes to mind in terms of where both volume and mass matter is transportation. You're carrying your fuel around with you. You care about how much volume it takes up and how much it weighs. And this is one of the challenges we see with long haul aviation and stuff. This is why oil dominates our transportation system, is because it's relatively dense by both volume and by weight. It makes it harder for hydrogen. It makes it harder for batteries, things like that. Okay, so I'm just trying to give you a sense of scale here. So if you're looking at natural gas as it comes out, this is on a volume basis versus compressed natural gas versus oil or coal, you can see the variation in energy density per volume. This gives you more energy density per volume ranges. So solar is going to be pretty low energy density versus something like uranium, extremely high energy density. And of course, I love little cartoons and graphs like this, where this is showing the energy density per mass, but of some things like coal and gasoline, and then uranium, where he's saying that log scales are for quitters. So showing that. One thing I do want to just, we're talking about energy density and oil dominating our transportation system, and I'm a big fan of electrification. You're going to get that sense through the quarter. But one of the challenges with electrification of something like airplanes is it's not just that the energy density differs, it's that when you have a liquid fuel and you're burning it in an airplane, you're actually lowering your weight through the flight. Whereas with a battery, that weight stays there, no matter how much energy it has in it, right? And so those are some of the challenges we see with long haul with batteries. Now, I'm excited. I have friends that are working on electrification of aviation, but it's one of those challenges. So it's how the weight of the energy changes throughout the flight. We're shooting it out as air pollution out the back of the airplane, and so the airplane gets lighter throughout the flight, and that's one of the benefits of burning a fuel for something like aviation. So just an aspect to think about. We'll get more into it. You guys have seen this before, but just wanted to bring it back together that we are talking about systems. We're not just talking about our resources, but we're talking about how we convert them and what we really want our services, right? So always keep this in mind. This is our goal. This is what we're trying to do. I mentioned this a little bit already, but a lot of times the most efficient thing is to match the energy resource to the use. So this is from one of my favorite books called, he has two actually, Solar Cat and the Return of the Solar Cat. The book is basically about how cats make better decisions than humans. It's really funny. But here's a cat that's cold and it goes sit in the sun and now it's warm. And here the human is cold and he's saying he's going to go get fossil fuels and uranium and a power plant to run his electric blanket. Just to kind of poke fun at how we're meeting our energy services. But again, it is an opportunity to make use of our resources like natural lighting and things like that to meet some of our services in a very efficient, low impact manner. You guys have already seen this too, but just to remind you, here's our two biggest energy systems in the world: oil for transportation, coal for electricity. And we're going to talk about this conversion efficiency. I mentioned that coal, we lose most of our efficiency right here. This is using heat for work. In the oil system, it's in your car. Again, using heat for work, we have a lot of losses there. And so what is our conversion efficiency? It's pretty simple. Thinking about how we measure conversion efficiency, it's basically our useful energy output divided by how much energy we put in, right, to get our conversion efficiency. It gives us a measure of our losses. So we're always thinking about how much useful energy we're getting out. Okay, so let's do some math for just a couple minutes. All right, so I've got two examples here. 200 joules of energy supplied to the hairdryer. You're getting 80 joules of useful energy out. Much of this, the wasted energy could be, it's not going to your hair, but also it's the noise that you have. The noise is energy that is not useful. How efficient is your hairdryer? Or you can do this one for a 1 horsepower electric motor. What's the input required? All right, has anybody figured out how efficient the hairdryer is? Hopefully most people got that, 40% for our hairdryer. Does anybody figure out the input required here? So it's about 900 watts. You have to do a little bit of conversion, horsepower, watts. So you'll get some practice doing that on some of your homeworks. All right, so just, so conversion efficiency again, useful out over energy in. We do a lot of energy conversions. So that's converting from one form to another in our energy systems. The way we figure out the efficiency of the whole system is we multiply those efficiencies times each other. So for example, if we have a coal-fired power plant, again, that's using heat for work, so pretty low efficiency. Making electricity through transmission lines, which tend to be pretty high efficiency. And then depending on your lighting service, this one is an incandescent light, you get about 1% efficiency for that system. You can do better with state-of-the-art natural gas power plants. They're a little bit more like 60% efficient. You can use more efficient lighting. You're getting more like an 8% efficiency. But I put this example here that efficiency isn't the only thing we think about, right? Because there are impacts depending on how you're doing it. So your solar panels might be 15 or 20% efficient on your house. You can use an advanced LED. It's less efficient, but it has other benefits. So we're going to talk about efficiency. We're going to talk about efficiency of systems. Just like we talked about energy density of our resources, it's just one aspect that you want to consider. But there's all sorts of other environmental, social impacts that you want to think about when you're making decisions. One of the things to think about, and kind of showed it in this example, is end-use energy efficiency can be very powerful, because if you're able to make the end use more efficient, you kind of have compounding savings going up because you don't have all of those losses all through the system. And so it's why a lot of times and we're going to talk a lot about end use efficiency in this class. It is why there's often a lot of focus on our buildings and things like that. If we can get our energy services with using less energy, same energy or better energy service using less energy, that's a really powerful way to reduce the impacts and the losses in our energy systems. I like to think of efficiency of solar panels as a land use problem, right? And so it's just basically how much land do you need to get that energy service. If you can make your panels more efficient, you need less space, less land. But if you're dual using your land like you are on your house or on parking lots or things like that, that has, to me, less impact than using it in utility scale, right? And so this is where you have to think about the value, not just these different aspects of the resources. Okay, so this is a little bit more busy chart, but kind of showing the same things of the energy conversions that are going on. Now our energy system is just going from top to bottom, but it's basically from getting your energy resource all the way down to our service and kind of all the stages it has to go through in between. I wanted to just bring up 3 kind of key ways, which we're going to talk more about this quarter, that we do energy transformations in these energy systems. The top, I've got turbines. That's wind turbines, hydro turbines, usually a pretty efficient way of converting from kinetic energy into electrical energy. So that's what those systems are doing. Heat engines, I'm going to talk about more. That's using heat to do work. Tends to be a pretty inefficient way, just inherently, physics in terms of heat engines. And then generators, that's where we're using mechanical energy and converting it to electrical energy. And we're going to talk more about how that works. But that's how we're, with our thermal power plants and any of our rotating systems, we're making electricity. So these are just kind of some of the technologies we're using to do those energy conversions. But let's talk about heat engines a little bit more because they're so prevalent in our energy system. Heat engines are what we're using to make electricity from any of our thermal power plants, whether that's nuclear, coal, natural gas, biomass. Those are all different ways that we're basically creating heat. We're boiling water in order to run a heat engine, a steam cycle power plant. It's also what we're using in our diesel, our gasoline engines, our jet engines. We're using a heat engine. We're burning a fuel to create heat to do work. Our heat engines use the natural flow of heat, basically, that heat is going to flow from a hot source to a cold sink, right? That's intuitive, right? Heat's going to flow. If you put something hot next to something cold, the heat's going to flow from the hot to the cold. Importantly, for our heat engines, you need both the hot source and the cold sink for this to work. I often get questions asked about why are we cooling down the system before we put the steam back around. It's a system. We'll look at that. You need both. It doesn't work unless you have that flow of heat from hot to cold. So what we can do if we have a hot source and we have a cold sink and the heat wants to flow, we can get work out of some of that heat as it's flowing from hot to cold. This is our useful work. This is our losses. If we're thinking about our conversion efficiency, right? So we would take our useful work and divide it by how much energy we put in to make hot. We have a lot of losses just inherent to the way a heat engine works. So I'm going to show you one of the most common ways that we make electricity. This is our steam cycle power plant. Our high temperature source, like I said, we're just boiling water, whether that's with burning coal or using a nuclear reaction or something, it's boiling water. That's our heat source. And then we have a low temperature sink, which is some sort of cooling water usually. It could be cooling water from the ocean. It could be a cooling tower, some way that we're cooling systems. So we have our hot source and our cold sink. We're running that steam through a steam turbine that's capturing that energy as the heat is flowing from hot to cold. And we're going to talk about this more, but we actually do that on a lot of stages. If you think about it, that cold is almost drawing that heat through. And so you actually usually have like a high pressure, a mid pressure, a low pressure stage in your turbine. You're trying to draw as much of that energy out as you can before it gets to your cold sink. And then it goes back around and gets hot again. These are steam cycle power plants. And that turbine is then turning your generator to make electricity. This, like I said, average is somewhere, 35% efficient. Some of our combined cycle power plants, which we'll talk about, are a little bit different, are more efficient, but for a steam cycle, somewhere around 35% efficient. You have a lot of losses inherent to it being a heat engine. Okay, so one of the things to know about these technologies that are converting from one form of energy to another, when we're talking about their efficiency, is that they can't get to 100%. It's not like we're trying to get to 100%, or that we can even reach there in an ideal world, let alone the real world. As I said, with our heat engines, losses are inherent to how we're doing it. We have to have some of the heat go into the cold sink and not be useful. And so the way to calculate the ideal world efficiency for a heat engine was this very nifty little equation that's pretty easy to do that is called the Carnot efficiency. Here's a little picture of Carnot, who came up with this. It's basically 1 minus the temperature of your cold sink divided by the temperature of your hot source. So if you're trying to think about, how do I make my heat engine more efficient? I can make my hot source hotter, and I can make my cold sink colder. Those are ways to make my system more efficient. And you can see this is a very important note, if you guys remember from chemistry class, There's a difference between our absolute temperatures and our Fahrenheit and Celsius. You have to use Kelvin or Rankine to do this calculation. So if you're given numbers in Fahrenheit, you have to convert it either to Kelvin or Rankine to do this efficiency calculation. But once you have it in that, pretty easy to figure out what is your ideal efficiency of a power plant or some other heat engine. I mentioned the different quality of our energy forms. Part of that, it has to do with how easy it is to make useful use of that form of energy. And the conversion efficiencies can be very different in converting from different things. So electrical energy has a very high quality, and you can see it's very efficient to be able to do things when you have electrical energy. Heat energy, if you're like doing mechanical energy, very low efficiencies, conversion efficiencies. Mechanical energy, you can do pretty high useful things with it. Okay, so just a way to kind of think about that. Kind of bringing this together about our conversion efficiencies and our technologies. I've just listed a few examples here. I mentioned some different conversion technologies and wanted to give you a sense of, like I said, we're not trying to reach 100%. This is a sense of what the ideal world, you guys know ideal world is like a world that doesn't have friction or air or anything. This is the ideal world efficiency of these conversion technologies, and this is where we are. And so when we're looking at this, for example, our solar PV at being 20% efficient for our single junction, we'll talk about what that means, but it's only, the ideal world is only 33 or 34%. So it's actually getting pretty close in terms of some of the records that we see, but it's 20% in the field-ish. You can see for our Kono efficiency of typical steam cycle power plants, of course, that's going to vary depending on how hot it is and how cold your sink is. Ideal world is somewhere around 60, we're 30 to 40%. Go enjoy your weekend. If you want to learn more about this topic or other energy topics, visit our Stanford Understand Energy Learning Hub for free resources, including signing up for our monthly Energy Spotlight. Don't forget to subscribe to our YouTube channel and tap the notification bell to be notified for our newest content.